properties of radioactive decay. Let's first look at the dice decay analogy. Consider there is 1,000 dice inside a box. Dice means 骰仔. In a flow, the dice with phase 1 will be taken away, or we say decay. In this case, the probability that a dice will be taken away or decay in each flow is P1 equal to 1/6. In the experiment, the number of dice remaining n and the number of dice taken away delta n in each flow are recorded in the table. Then we use the result in the table to plot a graph of number of dice remaining and against the number of flow from the experimental result. The curve shows that the number of dice remaining decreases when the number of flow n increases. More interesting is that the ratio of number of dice taken away to the number of dice remaining, that is delta n over n, for the first flow is about 160 over 1,000, which is approximately equal to 1/6, which is the same as the probability that the dice will be taken away in each flow. By tracking the ratio of delta n over n for the next flow, we have delta n over n equal to 128 over 840, also approximately equal to 1/6. Simply speaking, we say the number of dice decays per each flow is directly proportional to the number of dice remaining. Or we say delta n equal to Kn, where K is the decay constant for the dice. In this example, K is equal to the probability 1/6. Notice that not all the data points will lie on the curve because the decay of the dice is a random process. That means in each flow, each dice has the same probability to decay, but you cannot say for sure which die will decay in each flow. Now let's compare dice decay and the real radioactive decay. In a dice decay, the decay substance is the dice. In radioactive decay, the decay substance is unstable nuclei. For a dice decay, we say the probability to decay in each flow. In this example, this is 1/6. For radioactive decay, we say the probability that an unstable nuclei decay per unit time, which is K. And the value of K depends on which kind of unstable nucleus it is. The dice decay curve also represents the decay curve of radioactive nuclei, where n is the number of unstable nuclei left and T is the time. For the dice decay, the decay process is random, which means that you cannot predict which dice will remove in each flow. For radioactive decay, similarly, we say the decay process is random, which means that you cannot predict which nuclei will decay at a certain time. If the experiment is repeated, the data will fluctuate due to random decay. However, the shape of the decay curve will remain the same. The decay curve for a certain radioactive source is shown in the diagram. Let n be the number of undecayed nuclei. T be the time taken. The decay curve is an exponential function, which means that the number of undecayed nuclei n at time t is given by n equal to n naught e to the power negative kt, where n naught is the initial number of undecayed nuclei. K is the decay constant. Let's define activity is the number of nuclei decayed per unit time. Similar to the dice decay, we have activity A is proportional to the number of undecayed nuclei n. Therefore, we have A equal to A naught e to the power negative kt, where A naught is the initial activity. Mathematically, the activity A is related to the number of unstable nuclei left n by a formula A equal to Kn, where K is the decay constant. This formula is very important. You must memorize this one. What is half-life? 半衰期. Half-life is the time for the unstable nuclei to decay by 1/2. How to find the half-life? Method 1, by using formula. Since n equal to n naught e to the power negative kt, we have n over n naught equal to e to the power negative kt. When time equal to half-life, n becomes n naught over 2. Therefore, we have 1 over 2 equal to e to the power negative k half-life time. Log 2 equal to kt half-life. Therefore, we have the half-life for a radioactive nuclei is equal to log 2 over k. This equation is very useful. Notice that the half-life only depends on the decay constant. An unstable nuclei with greater decay constants will have a smaller half-life. If we use A equal to A log e to the power negative kt to find the half-life, then we have A over A log equal to e to the power negative kt. At time equal to half-life, we have the activity equal to A log over 2. And we get the same formula for the half-life time. Therefore, half-life has another definition. We can say half-life is a time for the activity to decrease by 1/2. Method 2. We can use graph to find the half-life. First, is to understand the meaning of measured count weight and corrected count weight. First, measured count weight is the number of radiations recorded by the GM counter per unit time. Unit time means per second, per minute, or per hour, etc. Corrected count weight is equal to the measured count weight minus the background count weight. That means correct count weight is the radiations emitted by the radioactive source only. If we have a graph of corrected count weight against time t, and that the initial activity is A log, then read from the graph, the activity drops to A log over 2, and the time taken will be equal to the half-life. Again, if the activity decreases from A log over 2 to A log over 4, that means the activity also decreased by 1/2. And the time taken during this time interval is also equal to the half-life. That means the total time is 2 half-life. Similarly, if the activity drops further to 1/2 to A log over 8, the time taken is also equal to 1 half-life, and the total time taken from A log to A log over 8 will be 3 half-life. Notice that the half-life time is a constant value for a certain radioactive source. This is the properties of exponential curve. If we plot a graph of measured count weight against time t, then the graph will be different from that before. The flattening part means that the activity is due to background radiation. Or background count weight. Mathematically, the half-life is found by using the time interval for the measured count weight drop from A log to A log plus AB over 2. This is the half-life. Example 1. The half-life of some radionuclides are given. Find their decay constant K. Since half-life equal to log 2 over K, we have K equal to log 2 over half-life. For uranium-235, K equal to log 2 over 7 times 10 to the power 8 years equal to 9.90 times 10 to the power negative 10 per year. For carbon-14, K equal to log 2 over 5760 years equal to 1.2 times 10 to the power negative 4 per year. For iodine-131, K equal to log 2 over 8 days, which is equal to 8.66 times 10 to the power negative 2 per day. For sodium-24, K equal to log 2 over 15 hours equal to 4.62 times 10 to the power negative 2 per hour. For radon-220, decay constant K equal to log 2 over Example 2. Let A lot be 2.4 times 10 to the power 7 BQ and A be 2.2 times 10 to the power 7 BQ and time T is 1 day. Part A. Since A equal to A lot e to the power negative KT, A over A lot equal to e to the power negative KT, we have log A over A lot equal to negative KT. Therefore, log 2.2 times 10 to the power 7 over 2.4 times 10 to the power 7 equal to negative K times 1. Therefore, K equal to 0.087 per day. Part B. The half-life of the sample, T half-life equal to log 2 over K equal to log 2 over 0.087 days. Therefore, the half-life equal to 7.97 days. Part C. Let A lot equal to 2.2 times 10 to the power 7 and A be 10 to the power 7. Again, we apply the equation log A over A lot equal to negative KT again. Then we have log 10 to the power 7 over 2.2 times 10 to the power 7 equal to negative KT, where K is 1 per day. Therefore, the time lit T equal to 0.788 days. Bear in mind that the product KT is dimensionless. That is, there is no unit for the product. If K is in the unit of per day, T must be of unit days. For example, if K is in the unit of per second, then T must be also of the unit of second. bear this in mind. Example 3. Since background radiation can be ignored, the half-life can be found from the graph directly, which is the time for the activity dropped from 80 to 1/2, that is 40. And we can read the half-life directly from the time axis, which is about 3.5 days. Example 4. Part A. Why do the data points not lie on the graph? The reason is that the decay process is random, or we say due to random decay. Part B. The background current rate can be read directly from the graph for the flattened part, which is approximately equal to 40 counts per minute. Part C. We have initial activity A lot about 540 counts per minute. Since there is background radiation, therefore the y-axis shown is the measured count rate. We have A lot plus AB over 2 equal to 540 plus 40 over 2, which is about 290 counts per minute. Therefore, the half-life can be found from the graph. The time for the activity, the measured count rate, dropped from A lot to A lot plus AB over 2, which is 290. Therefore, the half-life time is approximately equal to 4 minutes. We all know that the activity of a radioactive source dropped by 1/2 after 1/2 lifetime. Then, what would be the activity after n half-life? Obviously, the activity after n half-life to the initial activity is equal to 1/2 to the power of n. This equation is very useful. For part B, we have an over a lot equal to 1 over 2 to the power n again. Now an equal to a lot over 10. Therefore, we have a lot over 10 over a lot equal to 1/2 to the power n equal to 1 over 10. Therefore, n log 1 over 2 equal to log 1 over 10. Therefore, we have n equal to 3.32. As a result, the time taken is t equal to 3.32 times 8 equal to 26.6 days. Example 6. First, we have initial activity A lot equal to 3 times 10 to the power 10 EQ. The half-life is equal to 24 hours and the time taken is 1 hour. Therefore, number of half-life taken N equal to 1 over 24. By using the equations A n over A lot equal to 1/2 to the power n, we have A n over 3 times 10 to the power 10 equal to 1/2 to the power 1 over 24. Therefore, its activity after 1 hour is A n equal to 2.91 times 10 to the power 10 EQ. Example 7. What is the difference between activity and measured count weight? In fact, activity is a measure of the number of decays per second. However, measured count weight is the number of radiations measured by the GM counter per second. Part B, because not all the radiations emitted during decays will enter the GM counter. That means some radiations cannot enter the counter. Therefore, measured count weight is always less than the activity.